Hello everybody, welcome to video number 3 about how to make a computer. In video number 2 we tried to program this memory chip. We tried to write 5 bytes of data into this memory chip, and these 5 bytes of data were consisted of 3 instructions. The first one was put byte CC to the register A. The register, if you remember, is a place of memory in cell of memory in the computer, in the CPU, and registers have names. For example, A, B, C, D, and one of them is A. So the first instruction, it is altogether we had 5 bytes of data, and we have changed in video number 2. We changed this byte AB into CC. That was in binary, if you remember, 11001100. That's what we're having here. If we put voltage to this computer, for example, 4 volts, 4.5 volts. So we have here 11001100. That means CC in hexadecimal representation. And so we have written these 5 bytes. We wrote them by hand using a breadboard. In this video we're going to learn how to do it faster, not using breadboard but using a controller. And we're going to write faster, and we're going to make programs faster. We're going to write them to the memory chip automatically, not by hand. But before, what we're trying to do, so we have 5 bytes of data sitting at the memory chip. The first 2 bytes represent that like this: load to the register A byte, not AB, but in our case that's CC hexadecimal. That H means hexadecimal. You remember that 0x means hexadecimal number CC, and also H in the end means hexadecimal CC. So the program we have programmed in the last video, in the video number 2, was these 5 bytes, and they mean these commands: load to the register A byte CC, and output this byte CC, the content of the register A, to port 56 or whatever port. We are not using this. And the last instruction is halt, stop. And this port, this outputting to port essentially means the content of the register A is being sent to the data bus. And since the data bus is connected, the CPU should send the content of the register A to the port 56, for example. That means that 56 are going to be sent here to the address bus, and the content of the register A is going to be sent here by the CPU to the data bus. And also, since it's connected to the flip-flop, and when the CPU is sending something out, it's drawing to the 0 these 2 pins. They go here and connected here, and for him that means like pressing capture button of the camera. Usually this pin is high, and when CPU is outputting something, it brings it makes it low, and that's the moment that the flip-flop reacts. It copies, it duplicates the input. In our case, it's byte CC, and puts it to the output, puts it here. And then the CPU has finished outputting. It's releasing this capture button as example we can use, and then it's getting high, and then whatever changes on the data bus, it's not going to be reflected here. So we have CC sitting here just like this. But you can see it all in the video number 1 and number 2, how this works. You can build yourself something like this, and just you need some soldering skills, and as a power source you can use a charger from your phone. For example, you have 5 volts there, you can direct them here. This guy works from 3.7 volts something to 5.5 volts, all of them. They are pretty tolerant. So what we're going to do now, we already know how to output here something. This something is byte CC in our example. We don't want CC, we want some music at the output, and we're going to work only with 1 bit, only with D0. You see D0, that's D0, that's data 0. It's present at the memory, it's present at the CPU, and it's present at the flip-flop and on output. So this 8 bits, and we're going to use only the first one, and we're going to sometimes name it signal wire, because it brings information that can be 1 or 0. So they are all signal wires, they can be 1 or 0, and this is the ground. Since it's connected to ground, it's everywhere is ground at this side. At this side we have ground, and at that side we have, which is connected to here, we have some information, 1100 1100. That's the data bus. It's connected here somewhere and here somewhere. Yeah. So we want to work only with bit number 0, sorry. That's only with this one. Now it's 0. It can be 1 or 0. If we take a speaker and we'll give it 1, you hear something, you heard something, and we give it 0. We give it 1, we give it 0. We give it 1, we give it 0. But what if we do it 50 times each second, for example, or 1000 times a second, these ones and zeros? What if we change them 1000 times a second? We have this guy that we are familiar with, that's scope, and it is able to make this frequency. Its purpose is to measure frequency, to show what's going on the wire, on the high frequency wire, but it's measuring waves, but it also is able to make waves itself. But it can give, here you see ground, and here you see a signal wire, that signal wire, that means that in this case it's 1 kilohertz, like a wave. It's going to be 1 and then going to be 0, 1 and going to be 0, and that goes 1000 times, 1000 jumps each second. What if we connect our speaker to this frequency? First of all, we want to see this frequency, how it looks like graphically. We connect this probe, his probe, to 0, and another one goes to signal wire, and we want to see what it looks like with this 1000 hertz, 1000 jumps a second. It looks like this. And if you want to know, if you want to check frequency, we select frequency, and you see is 1000, 1 kilohertz. That's 1000 hertz. That's 1000 times a second. 1000 jumps a second, each second. So fast we are not able to put 1 and 0. We are not able to do so this 1000 times a second. That's too fast, but it can do that. And if we connect speaker to it, so this 1000 times a second, we're going to hear. You can hear that. That's these jumps, they generate this sound. And the more the frequency, not 1000 but 2000, for example, the more the pitch, the higher the pitch here, the higher the frequency we're going to hear. Human ear can accept frequency from, for example, hearable frequency. Human ear can hear from 20 hertz, for example, until 20,000 hertz. So in this range, we can put any musical note, any audio note, and all of the sounds that we hear all around can be put in this range from 20 hertz. Hertz means times per second. That's 1010, and until 20,000. That's 20 kilohertz. So in this range, we're going to we can change this frequency number of times per second that we're having ones and zeros, and from that we can changing this frequency, we change what we hear, what note we hear. So it can be different. It can be any music that we can make using different frequencies, making different frequencies. So we want this frequency here at bit number 1. This 8 bits from 0 to 7 mean 1 byte, and you can watch it in video number 1, video number 2 about this. So we want to work only with bit number 0. That's data bus number 0, data pin number 0. That's the first diode. It can be 1 or 0. So we're going to Now we're having here 0. We want to have 1 and 0. So we're going to change the program that we have written. Let's put it into Excel table. It's freeware Excel table. That's LibreOffice Calc. And we will make sections, logical sections. We will call these labels, like titles. I will explain later. Label, the first column. The second column is assembler. What means assembler? Assembler is language. You see these words. That's assembler. And this, you see these numbers. That's machine code. And assembler and machine code is just one and the same thing. Assembler and machine code is the same thing. Only this assembler is designed for human, and machine code is understandable for machine. This is understandable by human. This is understandable but by machine, by CPU. And this is the same thing. So we're going to put assembler here for us to write the program. We cannot think in these codes. We better think in this load A CC out to 56A. That's easier for us as humans. So we can put here assembler instructions one by one, filling this column, and the third column is going to be code. That's machine code. Translation to the machine code of this assembler instruction. These assembler instructions are translated to machine codes. So, and here we put address. Each this number has its own address in memory, as you remember. For example, 3E lives at address 0, CC lives at address 1, D3 lives at address 2, and so on. So that's address in memory, and we're starting from assembler, and we write this program one by one, all the instructions. Load A CC, load A. We're going to use CC. We're not going to use CC. We're going to output 1 and hexadecimal. I can use H like hexadecimal to show it's hexadecimal, but it doesn't matter. 1 in every numbering system looks the same. Number 1. So this is the first instruction consisting of 2 parts. Load to the register A, byte 1, and it's 2 parts, 2 bytes. The first byte describes the instruction, and the second byte is the data for this instruction, just like here. The first byte is 3E and the data is CC. 3E means put to the register A, next byte, and the next byte is CC. So we put here 3E That's the code, hexadecimal and 01 hexadecimal. So we have machine code for this instruction, load A1H. We have machine code, and they leave at address 0 and 1. We're going to use 4 digits. So this 3E leaves at address 0, 1 leaves at address 1. And label is like title for this section. And we will use it later a little bit. The second instruction, so we have 1 at the register A by now, according to this instruction. And after that, we're going to output this register A, the content of it, to the data bus, to the port number, whatever, 56, for example. Output to port 56 hexadecimal, content of the register A, just like here. And that's in machine language, that means D3 56 D3 hexadecimal 56 hexadecimal, and they live at addresses 2 and 3, 0002 hexadecimal 0003 hexadecimal. Yeah, and we can say in generally this is all is one function, single function. Its purpose is to output 1. It puts number 1 to the register A, and then sends this register A to the outside world. And so its purpose is to send to output to here 1. So we can name it this section like output 1, That's its purpose. Just a title for this 4 rows is output 1. That's the function of it, of this section that we have written. And the next section is going to be for example, halt. Like here, halt, that's 76. Halt, that's the assembler instruction, and its translation to the machine code is 76 hexadecimal, and it lives at address 4, 0004, like this. And we're not going to use labels for that. So we have one section that we can put some color here, background color. That means output 1. This section is designed for outputting 1. Put output number 1 to the register A and spit this register A to the data bus. spit out register A to the data bus. And now what we see here, so I'm going to use these borders. Maybe if I find how, this way, I think. Border, here we have borders like this. Now it's something, it's we don't need borders. You see this a little bit different from here. We have this byte number 1 CC. That's what we are outputting here. But we want it to be 1. Byte number 1, leaving at address 1, is 1. So we change it. We want to write, instead of CC, we're going to write 1. And we're going to take this memory chip out of the computer, put it to the breadboard, these legs are, better be careful with them. They are so fragile. I think I'm going to use some protection for them. It's not on. I think I'm going to use some protection for legs, for the legs of the memory chip. We have such holders, just like this. I will put it into this. Oh, it's too small. I think I have another kind. These are bigger ones, I think. That will give some protection for these legs, because if you break the leg of this memory chip, then you can hardly fix it, and they are not too cheap to, so we're going to protect just like this memory chip. If we destroy one leg from here, it's no problem. We have lots of these adapters, but we don't want to damage the memory chip, so we put it like It doesn't want to sit here. So I have to hold this, I think, in place when I'm going to write something on it. I'm going to hold it by hand. So give some voltage here. And we're having it's a little bit strange to work this way. Okay, I think I'm not going to use this adapter right now. We're going to be careful with these legs. Just going to be careful. If you want to find these adapters from electronic store, you can search them by keyword deep case maybe. So DIP abbreviation, that means this I don't know how to say, this format, this spacing, this protocol. That means this kind of legs. That's deep. So now we're going to change the address to 1, because at address 1 leaves CC. We don't want this CC, we want number 1 there. So at address 1 we're having CC 11001100, that's CC. And instead of CC we disable the output now, and instead of CC we're going to set here 1. Yeah, and that means that we put in all of the bits of the data bus of the memory chip to the ground, connect them to ground, except for D0. There from it has these legs from data bus from D0 to D7, and we're going to set D0 to 1, and that would mean 1, not only in binary numbering system, but in any binary in any system, numbering system, that would mean 1. All the rest we connect, all the rest bits we connecting to 0. Only bit number 0 is connected to 1. Now we are going to enable the writing just like this, and we're going to disable the writing just like this. We remove the number that we have set for writing on the data bus of the memory chip. We're removing it and we're checking it. Enable the output. Yeah, we're having 1 at the address 1. and we're removing the power voltage, and we can see this on our computer. Now computer must be, instead of CC, we must have one here. Just like this. And we're going to work with this bit number 0. We're going to have it 1, and then we're going to have it 0. We're going to have it 1, have it 0, very, very quickly. That's the frequency that allows us to. That's the way that allows us to write here any sound. Any sound we can then hear in our speaker by connecting this signal wire to the input of the diode, and the ground wire connecting to ground to here. And we're having nothing now, just some noise. But if we start to make something like this, 1 0 1 0 1 0 1 0, then we're going to hear something more interesting from the speaker. Yeah, and for that we're going to change our program. This is output 1, and we remove the halt. We don't want the CPU to stop, but we will copy this section, copy here. Instead of halt, we're going to have output 0. After outputting 1, we're going to have 0 at the output, and then we will jump to the beginning. We will make this loop, output 1, output 0, and then jump to the beginning, output 1, output 0, and then jump to the beginning, and so on. In this jumping to the beginning, now we will change this a little bit. This is the output 0, not output 1 in assembler, and that means in machine code output 0. And then, yeah, now this is output 0. This code for the computer means output 0, and for the computer this code means output 1. And now we're going to jump to the beginning. How do we do that? In assembler language, it is possible to write jump like JP, and then we want to say where do we want to jump. We can say it by putting address. We have these addresses here. Oh, sorry, this one must be 4 digits. And we need to use 4 digits. For example, we can write it like just like this: jump to 0000H hexadecimal, and that would mean jump to the address 0 JP 0H. That means jump to the address 0. We can write it like this, but also we can use label. In our case, we're not using a software named assembler. I'm going to use this software named assembler. That will allow me to work much faster, to write this program much faster. I don't have to write these machine codes. I don't have to watch that's about these addresses, to pay attention to these addresses. I don't have to use these 2 columns. If I'm using special program, I don't need these two columns, if I write in assembler software, I can concentrate on this. And instead of jumping to address, I can write jump to label, to output 1, for example. Put 1. And then I can say let's move this let's do that later. We will write jump. We will write this by hand, and we need to translate into machine code this jump output 1, and the translator is we ourselves a translator, but it is easier that the software will do this for you, the translation job. But now we're going to translate ourselves. How do we do that? Jump has some code, some machine code, and we can search it in the web. If we put our CPU short name Z80, and then we'll put instruction set, we will find what code has jump. Let's put it here. Into search JP. We want to jump, and we have this jump, and 2 bytes follows. This is the code that we want. That means C3. C3 means jump to some address. That's C3 hexadecimal. That's the code. And also it has 2 bytes to show the address. And we have these 2 bytes, 0000, 00, hexadecimal, 00, hexadecimal. Why this jump uses 2 bytes to jump to? Because it's good to have 2 bytes instead of 1. 1 byte is only 255 maximum. From 0 to 255, 1 byte can be. But if we have a large program, if we had a lot of code, 255 addresses, that's too little. That's too few. We want 2 bytes at least. So this jumping works with 2 bytes, and these 2 bytes are zeros, 0 and 0. That means the beginning. In machine code, we have some weird rule that the first byte that we write is the last byte. If we want, for example, to jump to output 0, that is, it's not 3, it's 4. Its address is 4, then 5, then 6, then 7. We will remove this. Let it be. So if you want to jump to address 4, which is labeled by output 0, then we would write this like C3 0400. It should be C3 0004, like here 0004. But in machine code we have some strange writing rules that when we jump somewhere, we need to put the last byte to the first position, and the second byte to the first position, and the first byte to the second position. So we need to swap them. the first and the second byte. So that would be jump to the address 4. That would mean C3 0400 hexadecimals. So we can use labels if we don't want to deal with machine codes or addresses. We can use labels, but we need to have some software. We need to download some software named assembler for this type of processor, Z80, and we will later start using it. But now we want to jump. Oh, sorry, I have removed this important thing. And this jump leaves at address is 808 hexadecimal 0009 hexadecimal and 000A hexadecimal. Why A instead of 10? That's because it's hexadecimal. You can learn it from video number 1 and video number 2. Yeah, that's our program. Output 1, output 0, and jump to the beginning. Yeah, I hope you understand so far. So we're going to change the code here. We're going to use our software. We're not going to use this anymore. This by hand, this programming. We're going to use our software. And we're going to use a controller. You already know how to write these bytes to here. You can do it by hand using a breadboard. It's very easy, like you see, but it takes a lot of time. So we're going to switch now to the faster way. It's not necessary, but it can make it will allow you to work much faster. So what we're going to do, we're going to use software assembler. It's named assembler. I have this development environment that's named Z80 Simulator IDE, and it has assembler software. It is I will remove this one. This software can translate your commands, your instructions, these ones, assembler instructions, into machine code. Let's, for example, copy with labels them. Let's put it to Notepad that it would lose its formatting, just like this. And now we copy Control A, Control C. We copy this into assembler. You can find different assemblers for the Z80 from the internet. So now we're having output 1 section, output 0 section, and jumping. Now we want to translate this into machine code, and for that we're pressing F8. Yeah, we have successfully translated them. At address 0 we have 3E, at address 1 we have 1, at address 2 we have D3, at address 4, at address 3 we have 56, at address 4 we have 3E, at address 5 we have 00. We can compare to these ones. 3E1 D356, 3E1 D356, 3E0 D356, 3E0 D356, C30000, C30000. Number of errors 0. And this assembler has made this code for us, and it also made a copy here, or sorry, into memory editor, where we can grab it. 3E01 D356, 3E00 D356, C30000, and we will select all, we will copy, we will put to notepad, just like this, and we will remove the junk. C30000, that's our jump, and we will remove the little bit later we will remove this junk, this piece of junk, but now we're going to replace Ctrl H. Using Ctrl H, we're going to replace spaces with comma space 0x, like this, and that means hexadecimal. 0x means hexadecimal number, and this is important for one software which you have seen already, and its name is Atmel Studio. Atmel Studio is a place, is a editor, text editor. We can say, we can name it this way. That, so we have written these bytes, our program here, output 1, output 0, and jump to the beginning. It's output 1, then output 0, and jump to the beginning. So what is this? This is the program written in C language. This is machine code that we have created using assembler. We have written the program in assembler, like you see. Like you see, this is assembler, and this is its labels for jumping and for dividing sections. So this assembler and labels we copied into the assembler software. You can find different softwares in the web. That's assembler software. We have copied labels and assembler here, and this assembler software is able to translate. If we press F8, this software translates this language, our program, into machine codes. And these machine codes, this software puts to the place named memory editor, and here we have grabbed them, changed a little bit, like 0x, added, and put them into this software. This software is written in C language, and we have put here our bytes to write to memory chip. And who is going to write them? The guy, his name is controller. This controller has legs. It has a lot of legs, and each leg can be 1 or 0. And if we want to write something using, like, for example, breadboard, then we will change legs all the time. If we want to write something here, we change state of the legs from 1 to 0 or from 0 to 1. And it's very convenient if we connect his legs to his legs and we teach this guy. This controller is computer in principle. This is computer. It has a CPU inside. It has read-only memory inside. It has clock inside. This computer can be instructed, can be taught, and this is the teaching for him. This is the instructions for him that teach this guy to write this stuff into here by setting his legs to ones and zeros in the right time. So it can do it much faster than we do it by hand. And now we're going to protect. We're not going to use this breadboard. Yeah, we have 2 legs missing here. I'm not sure that we're going to find them anymore. Oh, here they are. I'm going to put them back. Just we want to protect the legs of our memory chip from bending, from breaking. Yeah, let it be like this. So it's now like legs are protected, and we want for in some degree. Now what we're doing now, this is our memory chip. We're connecting its legs with his legs. This is computer. We can teach him to change state of each of his leg to be 1 or 0, and since they are connected with his legs, this guy can control its legs. Each leg can be 1, it can set to 1 or 0. So now we have put them at the top of each other, and now we're giving some. Here we have 4.5 volts. That's enough to write something here, but this guy, we need to connect to this software using this computer, and there one more guy that we have here. His name is USB ASP, a little bit modified. and he's going to be like a mediator between computer and controller. So it's going to translate into, it has plus, ground, and two uh, wires that are connected to two of the legs for programming this guy. So this instruction how to write this stuff is going to come here, and it's going to learn how to write our bytes into the memory chip. And we're starting this communication between our computer, where we have these bytes, and we're going to teach just like this. Yeah, everything is fine. And now we have instructed this guy how to write our bytes into memory chip. Now we want to give some more voltage here. This plus and ground are connected with this plus and ground. Just the computer doesn't give enough voltage for writing, and we need some more voltage. That's why we give it here. And now this guy knows already what to do, and it's writing. Yeah, it has written this code into the memory chip. Now we will check it. And as you remember, we have output 1, output 0, and jump to the beginning. Output 1, output 0, and jump to the beginning. And that's forever. If we take a look at what we have here, it looks like 1, doesn't it? But it's not. It just looks like 1, but it's not 1. It's changing. 1, 0, jump to the beginning. 1, 0, jump to the beginning. And to check it, to prove that, in order to prove, we're using the scope. We want to see what's going on this bit number 0 of the data bus. So we connect this probe that must be connected to ground. We connect it to ground, just like this. And we're going to watch the input of this diode. What's going on there? Yeah, that's what's going on. And we try to zoom out. Yeah, you see these beautiful blocks. This is 1, 0, jump to the beginning. 1, 0, jump to the beginning. When it's jumping to the beginning, it's 0, because because when it's jumping, it's not outputting. And the last thing that the CPU outputted was 0. And this one remembers this 0, this photo camera. That's why it's 0 is longer than plus. 0 is longer than 1. So we have this beautiful thing, but frequency, but the problem is that it's too fast. They come too fast. we are not able to hear because the frequency is 40 kilohertz. That's 40 jumps, 40,000 jumps each second. That's too much. We cannot hear by our ear. Our hearable frequency is, as you remember, from 20 hertz to 20 kilohertz, but it's 40 kilohertz. So we need to we need to delay the CPU. Just the same way like jumping takes time. That's why it's got longer here. We want to make the CPU do some useless stuff just to waste time between these jumps. And for that, we're going to use registers. We're going to use registers we already know how to use register A. We see load A1 and then spit out this A to the port 56. Load A0, load 0 to A, then spit out to the output outside world. Load 1, send it to the data bus, load 0, send it to the data bus, load 1 to the send it to the data bus, load 0 to the send it to the data bus. So we are loading into the register A. Register A is like a pocket for us, and it's a memory cell of the CPU with the name A. But besides A, it has a few more registers that we can use. The same way like we're using A. It's B, C, D, E, H, L. So we're going to use register B, and we're going to make delays between here we will put name it like delay frequency from 1 frequency, because we want to work with frequency. Frequency is too high. 40 kilohertz is too high. So first of all, let's do this way, that we load into the register B, LD B. We load to the register B. The maximum that we can load is 255 in decimal. That's FF in hexadecimal. That's the maximum value of 1 byte, 255. That's FF, or 1111, 1111 in binary. That's 8 bits, 8 ones. So we have loaded 255 into register B, and now now we have label, and now we have decrease, that's decrement B. That means that after decrementing the B, the value of B is going to be 254. If we decrement once more, then the value is going to be 253, and then 252, 251, and so on. So the decrementing is -1. Decrement means -1 for B. And after that, we're going to jump if this is if register B is bigger than 0, then decrement once more. If register B is bigger than 0, then decrement once more. If the register B is bigger than 0, then decrement once more, and it's going to loop 255 times, and after that the register is going to be 0, the register B, and then the condition would not fulfill. I will show what command it is. It's conditional jumping. JP, if not 0, then to delay frequency 1. Yeah, like this. So we have 255 at register B. After decrementing, we have 254 at register B, and then goes compare. If the last operation before this resulted in 0, oh sorry, if it hasn't resulted in 0, then jump to the delay frequency 1. That's decrementing B. If decrementing B hasn't resulted in 0, then jump once again to decrementing B. If decrementing B hasn't resulted in 0, then jump once again to the decrementing B, and until B reaches 0. You see, that's going to waste time. The CPU is going to waste time. 254 times it's going to do something useless. After that, this condition will not this condition will not pass, will not work, because this jumping if not 0 will not work, because B is 0, and if this condition is not fulfilled, then it will not jump, then it will fall to the next instruction. So you see this delay. The point of this delay is wasting time in loop, decrementing this B until it reaches 0. So that's the this is the even this for rows mean wasting time. Yeah. So we have delay now. Now we're going to see how we're going to translate it into machine language. The translation has went successfully, and it also copied somewhere to the place named memory editor. Let's select all. Let's copy. Let's remove. Oh, sorry. Let's paste into the notepad. All this stuff, including rubbish, and let's remove the rubbish from here. The last thing is jumping to 0, to the beginning. Let's remove the rubbish. And let's replace spaces with comma space 0x, just like this. And now it's ready for Atmel Studio, which will teach this guy to write into this memory chip. So we will copy this, our program, translate it into machine codes. We will copy into Atmel Studio. Instead of this, we have a new version with delay, with wasting time section. The CPU is going to waste some time before writing 0. Yeah, just like this. And we now want to write these bytes into memory chip. So we connect this memory chip with the controller with our computer, this little computer. And now we're going to teach this little guy, this little controller, using the Atmel Studio. Sorry. We're going to start it up. Now we're going to clean the cache or whatever. Then we're going to execute this teaching. Well, it has not succeeded. I think that we need to disconnect this and connect once again. Then let's try once more. It's cleaning. No, it's not working this way. This one we don't need here. We'll stop. Then we will disconnect. We will connect once again. It works somehow. It's not so good that it is. It works not so good, but it's much faster than writing bytes manually. I think I have to restart this. I think I have to restart this Atmel Studio. Also this. Sometimes it seems to me that the computer doesn't give enough voltage to the USB port, and maybe that's the case because this guy is pretty hungry. It draws a lot of current, but we will try. If it's not going to work this time, then we will disconnect the scope from the computer. So now we starting Atmel Studio, and now we try to clean up. Now we try to write. No, it doesn't work. So we're going to disconnect this guy. We're going to use this port. I don't understand why it's red. Everything seems to be okay here. Let's try once again. I don't know. It just doesn't want to work. Seems like connection is quite good. Yeah, let's try once again. Starting the Atmel Studio. And here. And here. Yeah, this time is something better. We have something better. Let's try this one. Yeah, this one has worked. We have taught this guy to write our bytes, our program, with delay, with wasting time, with CPU wasting time, to this memory chip. Now we're going to give some more voltage here. We give more voltage, 4.5 volts. Now we're waiting while this guy is writing our bytes here. Now it has written our bytes successfully, like it shows 5 lamps, green lights. That means that everything is fine. Now let's see how this delay looks like. If you remember, the last time we had 40 kilohertz of frequency. That was too much. We're not able to hear 40 kilohertz, and now must be delay. We need to use this guy once again. And let's see what's going on the input of on the output of the computer. We will connect this probe to the input. Yeah, you see this strange picture, these squares. That's really not a square, but it's also changing signal from 1 to 0 and from 0 to 1 is shown here, but you see these vertical lines. That's the jumpings from 1 to 0. That's where you see this vertical line that's jumping from 1 to 0, and 0 is very, very narrow, and the 1 is very wide. Why? Because of the delay. You remember that we have delay, we have delay, this wasting time section, after we output 1. We output 1, then flip-flop holds this 1, and when we don't output anything, the CPU just wasting time, then we're still having 1 at the flip-flop because it remembers the last thing that was outputted. And after that we output 0 for a little time, and we jump to outputting 1 once again. So the 1 takes almost all the time. It's almost all the time is 1, and just for a little time it's 0. And the frequency of these jumps from 0 to 1 it must be much lower than 40 kilohertz. The last time we had 40 kilohertz, now we have it's connected more reliably. Now we have 500 hertz. Like you see, that's 80 times lower frequency. Thanks to this delay, thanks to this wasting time, we have 80 times lower frequency. And that's 500 hertz is nicely inside this range, hearable range that we can hear. Now we will hear this 500 hertz. If you remember, we had 1 kilohertz here at the scope coming out. That was 1000 hertz, that 1 kilohertz, that means 1000. And now we have 500, that's twice. Yeah, you hear that? That's 500. And now what we're going to do, we're going to make one more delay after we're outputting 0, because it's no good if almost all the time we have 1 at the output. We're going to change it into something more beautiful. So after outputting 0, we're going to have one more delay. So we reload this 255 into the empty register B. We don't want it to be empty, we want it to be full. And after that we're starting to decrement, to waste time until it reaches 0, until the register B reaches 0 once again. And after that we jump. So let's see. So we have added one more delay after 0, after outputting 0. So let's see how, F8, it shows some error. We need to rename. We cannot have 2 labels with the same name, because the jumping doesn't know, the program doesn't know where we want to jump to replace this label. In the jump command, we cannot use labels. In the machine code, we need to have address, and this program searches for the label where next to what command it sits. It finds it here sitting next to decrement B, and it finds it here sitting at this decrement B, and it doesn't know where to jump. Do we want to jump here, or do we want to jump here? What address it's going to put? And now we're going to change it into delay frequency 2, and that would be unique name, and it knows where to jump. So F8, and now we have no errors. So let's take this code from here. Let's select all. Let's copy from here. Let's put it into the notepad. Just like this. Let's remove the junk. This is jumping, jump to 0. We want this 0. We would like to keep these zeros, but all the rest of the junk, of the rest junk. Now we replace like before. spaces with this 0x. Now we remove the last piece of junk. Now we have Control A, Control C, and we copy this into Atmel Studio. And instead of our previous version, we're going to have this one with 2 delays in it. So we're going to write into our write this code with 2 delays, 1 delay after outputting 1 and 1 more delay after outputting 0. And we're going to write it here into the memory chip using this smart guy controller that we are going to teach now how to write these new bytes. So this teaching is the same. It's a pretty big C program in C language, but the data changes. We are updating the data that this guy is going to be taught to write to memory chip. Now try this one. Now we have the same problem like we had before. Let's try to disconnect this, connect it once again, and let's start this one. Like this, and this. Yeah, this time it works. Yeah, now we will give some more voltage here. This guy already knows how to write these new bytes into the memory chip. We give it some more voltage, 4.5 volts, and it's going to write this for us, hopefully, into the memory chip. That will show if we have 5 lights here, then 5 green light. Yeah, that's written. It's been written. Our new version of program with 2 delays. We have put memory chip back into our computer. Now we will see how these 2 delays work, what these 2 delays look like. We will connect our scope like this. One probe goes to 0, to ground, and another probe goes to the input of this LED. This is the output of our computer. Now we're going to look at this. Yeah, you see, this looks much nicer, like this. Very nice. And you see this length of 0 is almost identical to the length of 1. That's because we have not 1 delay, but we after outputting 1, but we have another one, the similar delay after outputting 0. And the frequency is twice slower, 2 times lower. We had 500 hertz, now we have 200 hertz, 250 times a second we have this jumping. 250, yeah, 256 times a second. And we definitely can hear this on our speaker. If we connect our speaker somewhere here, yeah, just like this. Yeah, but what's the problem now? The problem is this, that it's indefinite. We want to stop this and we want to play another note. I believe we have two scopes. One is here. We want to stop this sound, and for stopping this, we want to use another register. We're going to load this register. It's going to be, for example, register L. We're going to put here 256, and so we have put here 256 into register L. It's going to keep it. It's going to output, it's going to delay, it's going to output, it's going to delay, output 1, delay, output 0, delay. And after that, we're going to compare. Instead of jumping without conditions to the beginning, we're going to make condition. First of all, we're going to decrement our L from 256 into 255. Decrement our L, and after that we're going to see what the value of L is. That's jump if not 0. Jump if not 0. Jump if not 0 to output 1. Then it's going to decrement L once again from 255 to 254, and then it will compare it to 0. If it's not 0, it will jump once again here to outputting 1, and it's going to decrease all the time this L until it reaches 0. So 256 times it's going to run through this program, output 0, output delay, output delay. It's going to do this 255 times, and after that it's not going to jump anymore. The condition would not fulfill. The register L would be 0, and when it will be 0, then this jumping will not happen anymore. And then we will put something like we will put another note here, another note, and we will name this. We can put comments here in assembler. It's very convenient if you put semicolon, and after semicolon you can write whatever you want. That's just for you. Note 1, for example, that's musical note 1, and this and this one is note 2. So it starts from loading 256 into L. That's loading 256 into L. Yeah, that's node 2. And we're going to change these labels. Output, instead of output 1, we will put output 1b. We need to have unique names, that this, when it's going to play a second node 255 times, it's going to jump here, not there. So that's why we changing these labels, that it would be local scope for these labels. Frequency delay 1v, for example, that's the destination for jumping. We will put to all the labels, for example, letter B. We would name it like B, and we would jump to this label, and in the end that would be B. That's the unique and after that, the unique label name must be like we discussed before. After that, we will halt when the two nodes have been played. We will halt. We need to have this space. If we write command, not label, we need to have this space. This is the rules of this software. So we will put, we will, oh yeah, we need a comma here. I have a mistake. I have made a mistake. Where is our mouse? I don't see my mouse anywhere. Oh, yeah, I see. So we need to have comma here. Just like this. And this one. I don't know. This one, I see here a mistake, that we forgot to put B here. That must be unique name. But why? We need it just like this. Output B, output 0B. That section begins with loading zeros to A and outputting zeros out to outside world. Then we have delay like this. We have one error here, must be comma, and yeah, just like this. Maybe we'll put them all together. Just just like this. We have two nodes. The first node is here, and the second node is here. They are similar. It's going this outputting 1, delay, outputting 0, delay, and then outputting 1, delay, outputting 0, delay, and that's 256 times. After that, we're going to play node 2. Output 1, delay, output 0, delay, and then jump once again here until the L reaches, until it reaches 0, and then halt. when it is 0. Let's try F8. We have some error. Which error? Assembly was not successful. Your assembler source contains 2 errors. Let's look at them. That's too many. 256 cannot be. 255 is maximum. This mistake. 255, that's the maximum value. That means FF in the hexadecimal representation. Now it's okay. Everything is fine. I can press once again F8. Yeah, everything looks good. Now we have 2 nodes with delays. Each one has 2 delays. After outputting 1 is 1 delay, and after outputting 0 is another delay. Now we copy this code to the notepad for cleaning. Let's clean it up. And we have halt after playing 2 notes, so we don't have zeros at the end. We have 76. This is the code of instruction halt. 76, that's the machine code of instruction halt, as you remember. So we're removing the junk. Now we replacing spaces with 0x, removing last piece of junk. Now let's try this. 2 nodes. Oh, sorry, I forgot one thing. We want to see difference between 2 nodes. That's why we're going to use different delays. The delay frequency, that's B, we're going to change. We're not putting here 255 for wasting time. 255 times it wastes time, but the CPU is going to waste its time 100, for example, 100 times. Going to be about two times less time wasting in the node number 1. It's going to do a useless job of this decrementing in place. The CPU is going to do this twice, 2 times. It's going to finish this wasting time 2 times faster. So it's going to run through this code 2 times faster. Output 1, output 0, output 1, output 0. It's going to do this 2 times faster because we have reduced the time, or the useless time. We have made these delays smaller, and it's going to run 2 times faster. And that would mean that it will play this note the note is going to be shorter. It's going to play it faster, to finish playing this faster than this note. You will hear that. So we're going to compile, translate it into machine language. I haven't seen that. Yeah, I have. Now the first node has delays which are smaller than the second node, and thanks to this we're going to hear sound of the first node is going to be higher, the frequency much higher than the second node. That we can see the difference between these 2 nodes. Sorry. No, we'll select all, and we will paste here this code, and we will remove junk from here. Like before. So we have two nodes. Each one has two delays, and delays of the first node are smaller than delays of the second one. And thanks to this, the first node will play in less time. It takes less time to play for the first node than for the second, and it's going to be with higher frequency. We're going to hear higher frequency sound of the first note. So we're going to write these new bytes containing two nodes to the memory. Let's remove this memory from the computer. Let's put it here. Let's connect it to our computer. Let's start this teaching process of this guy. We're going to teach him to write these new bytes to the memory chip that we've connected with him. Yeah, successful. Now this guy knows how to write these bytes, new bytes to the memory chip. We give some more voltage, 4.5 volts, and it's now writing. It started to do what it has been instructed in this C program. Now the writing was successful. Now these bytes are sitting here. This new version of our program is sitting here with two nodes. Each one has two delays, and the first node is going to be faster. It's going to take less time for playing it, and it's going to be with higher frequency. Yeah, you see, it's 1 and it's 0 because we have halt now. We have halt after we have stop. We have the instruction to stop after playing two notes. Now we're going to hear these two notes. I hope. Interesting. It's not very convenient. Yeah, like this. Yeah, you hear the first note plays in short time. That's because it plays much faster because delays are small. But what if we want it to play longer in longer time? What if we want to hear this first note longer? We want this first note to be longer. For that, this note 1, we're going to make longer. Now we have 255 times jumping from 1 to 0 here, and we have 255 times jumping from 1 to 0 here. But the problem is that we have smaller delays here. That's why this 255 times goes faster than here. But the problem is that the register L that have that we have loaded with 255, it cannot hold more. We cannot put here 700, for example. We are limited with 255. But we want to use external loop. We want to use one more register, and it's going to be helper. I will write it down and I will explain after that. I will I will put label here like delay what label I will put here? I will put here label let's see, have bigger program somewhere that I will later explain to you, and it has already labels here. That's duration delay. Let's name it duration delay. Duration. That's duration of the note. How long it plays. Delay. Duration delay. And before this duration delay, I will put, for example, 2 into register H. Or I will put 3 into the register H. Just like this, I will put into the register H 3. And then goes this part, and it's going to play 255 times here like before, but after that it's not going to jump to second note, but instead of that it's going to decrement H, which is now 3, and it's going to be 2, and after that, if H is greater than 0, then jump to duration delay. Duration delay. Yeah, that's the one. You see what happens here? Now we have H, which is 3. After that we play this part, we load 255 into L, and we start to decreasing this L with each jump 1 0 1 0 1 0 1 0 255 times. It's this L is greater than 0 255 times. It's decreasing, but it's still greater than 0, and when it reaches 0, when it's greater than 0, it jumps to output 1, but when it's 0, then this jumping doesn't work anymore, and then goes decreasing H, which was until now it was 3. Now it's going to be 2, and then if it's greater than 0, this H, which is 2 now, it's jumping to the reloading of L, which is going to be once more 255 times. After that, decreasing H from 2 to 1. After that, once more we load this L with 255 times, and after decreasing it 255 times, and after that this decreasing of H happens, and comparing to 0. If it's 0, then after that is going to be played note number 2. So we have L times multiplied by H. So it happens like this, just like this. We load H with 3, for example. Then what happens? We load L. We load L with 255. Then action, this jumping, and after that we decrease L 254, and then we will jump once again to here, and it's going to repeat until L is 0. And when L 0, then H, decreasing H to 2 and comparing it. If it's greater than 0, then we are jumping to here. In here, once again, we put to L 255 and start decreasing it until it is 0, and then we will decrease once more H. So we H, we put to H 3, then we put to L 255, then we will act this jump, send to the output 1 0 with delays, then we will decrease L 255 times, then we will decrease H from 3 to 2, then it will jump, oh sorry, in previous it's after decreasing L it acts, after decreasing L it acts, after decreasing L it acts, 255 is L, 254, 253, and so on until it reaches 0. Then we're decreasing H just once, and then we jump to assigning L to 255. Then we put once again 255. So it, I don't know even how to illustrate that. So L sits inside of H. L works from 255 to 0. Inside of L we have this jumping 255 times, and then H decreases from 3. It was 3. It was 3. Now it's going to be, after decreasing H, it's going to be 2. If it's still not 0, it's going to put once again 255 into L, and it once again repeats this from 255, decreasing to 0 until the 0, and then once again just one unit is decreased from 8. It was 2, now it's 1, and once again it jumps to assigning to L 255, and once again 255. So in a sense we have 255 jumps multiplied by 3. L is multiplied by H. Thanks to this, we have this much longer delay now, much longer number that can be played, this 1 and 0, this loop. Let's try that. We have two loops now. In the first node we have two loops, one inside another, L inside H. And in second node we don't need that because we have slower CPU, we have longer time of this, we have a longer duration of this node. So we don't need more than 255 this number to be. That's why it's enough for us to use L, just L. So let's see how it works. Oh, sorry, we need to play F8. Yeah, we have no errors. Let's see logically assign. Let's see how, if we don't have logical errors here. We'll put 3 here, then we will put 255 here, 3 to H, 255 to L, then L decreased somewhere somewhere here. If it's not 0, then output 1, output 0, output 1, output 0 until L reaches 0, and then decrease H, and if H is greater than 0, then put 255 once again into L and repeat. It's decreasing and playing ones and zeros. Yeah, seems to be everything fine in our program, and yeah, it looks like works. Let's select all, then copy, then let's put it for cleaning into our notepad. Let's clean it up until halt instruction. So it's very important that we have understood how to waste time of the CPU, how to delay, just decrementing some number, and also we have understood how to repeat a note how to repeat a note some number of, how to make it play some for some time. And how to make it play some number of loops, some number of times. So now we have extended our, comparing to the previous version of our program, we have extended our first note. We have multiplied this duration by H, by 3. It was 255 times it played. The jump was from 1 to 0. 255 jumps we had. Now it's multiplied by 3 in the first note. But the second note plays 255 times. We don't need it to play longer because it's slower. It takes more time to play second note, and it's okay. 255 times it jumps from 1 to 0. But for the first note, it's too fast, too quickly, too quickly finish this 255 times. That's why we have multiplied it by 3 by using H register besides L. We multiplied L by H times. H, not 8, but H times. H times of L. Now we instructing our controller how to write these bytes into, we have instructed our controller into the memory chip. Now we give some more voltage to the controller, and if we have 5 lights, then the job has been done successfully. We have 5 green lights. Now we put our memory back, our freshly programmed memory back into our computer, and the first note is going to be played 3 times longer. 255 multiplied by 3. That's how many times it's going to jump from 1 to 0, the first note, with smaller delays than the second note. We're going to hear, this one we don't need actually anymore, because we can detect it with our ear instead of scope. We don't need scope. You see, the first note is playing much longer now. We have achieved this task, that we extended the duration of our note from 255, have multiplied it by 3. 255 multiplied it by 3. We have encapsulated one loop into another. We can compare it with a clock, with digital clock, for example, with digital timer, which has 2 numbers. The first number goes from 9 to 0, then the second number is decremented just to 1 unit, just like this. But it's going forward, but when it goes backward, not 7, 8, but 8, 7, 6, 5, 4, and then goes the H. For example, this is our L and this is our H. So it's relation between them. This is much faster decreasing than this. It's a multiplied L by H times. Now, we're not going to use anymore the second note. We want to use just one note. I will explain. Actually, we have you see, we have 2 notes. One note, the first note, and the second note. Now we're going to make a template from this note. We're going to have 9 notes, for example, but with each note we're going to change delay, we're going to change duration delay, we're going to change frequency, delay duration, delay frequency, and we're going to I will draw it like this. This is our node. This is our node, like output 1, then output, delay, then output 0, delay, and this is our L loop. This is our H loop. Let's name it like this. Let's write it like this. So this is our program. Inside H sits L. Inside L sits this output 1 delay, output 0 delay. Like we have done until now, all this code we can represent like this. H time multiplied by L, we have this jumping on the speaker. Now we have like 20 notes. If we have 20 notes to play of our melody, we need to copy this 20 times. We need to use, for example, our note 2 is duplicate almost identical to note 1, except for this H. But if we use H as well here, it's identical almost to the note 1. But what if we have 100 notes? Then we have a lot of space to waste. You can waste it, you can do it like this, but you can reuse. You can reuse this note with little changes that you can make. What is difference between these two notes? I'm not talking about H. Let's say that it has H as well. These notes are identical, but this is different in that delay is smaller and duration is different. For example, not 3 but 0. It has 0. H contains 0 here, but we don't use it. But it's the same, like it would be 0. But some note may require 4 or 5 or 6, whatever, here sitting at H. And L can be different. So so we have with each note we have to change H, we have to change L, and we have to change B, like wasting time inside note, this delay. And this B we have twice. So we have to we have to set H, we have to set L, and we have to set B. If we set these numbers H, L, B, and that's note 1, and then we jump here, that's note 2, H, L, B, and then we set these numbers, and then we jump here, the same place. We jump at the same place because all the rest is identical. Only these values are different. But after playing this note, we have to return to the next note. If we have a lot of notes, we have to somehow we need to use some memory. We have to tell this CPU to jump back to the next node. Let's use a C register to hold reference to node 2. From node 1, we jump from after setting node 1, we jump to this playing, uh, and when this playing finishes, it will jump back. Where it's going to jump? It's going to jump where we tell it to jump to, and let it be C that holds this jumping destination for the next node. And so it's going to jump to C, and it's going to jump here. After playing this, it's going to jump to C, and the C it has node 2, and in this node 2 we have set C like node 3, and after that we jump here to playing node, and then it's reusing this code, and C now it has a node 3 inside, so it jumps to node 3, and in the end of node 3 we put reference to node 4, and then we jump here, and after playing this it jumps to C, that is node 4, and so on. So we can write much more efficiently using this, setting these registers instead of copying this outputting, delaying. And I have already this code. Let's copy this from the Atmel Studio into I have this code, node 1, node 3, and I have 9 nodes, and I have this playing node section. Let's translate it into machine language. Let's take a look at this. It's more convenient to look here. I will try to translate. Let's see, it has errors. No, there's no errors in it. Everything is fine. Let's see. To save time, to save space, you can use HL together. You can use, of course, load H and load L, but you can load HL. It's the same. Instead of 2 rows, you can use 1. And this 3 goes to H and 49 goes to L. In this case, it's 3 goes to H, 49 goes to L, with B different. We know that B means wasting time. This duration, this delay 1, delay 2, 2 delays after one, outputting 1, another one after outputting 0. So this is B, and HL is this times of jumping, these ones and zeros. So H multiplied by L, that so many times it's going to jump from 1 to 0 with delays. And C holds reference to next node. Node number 1, we set for node number 1 we set these loops HL, how many times jumping happens, and delay inside after outputting 1 and outputting 0. And we set also new register C to reference to the next node. After playing the node, the CPU knows where to jump to. After setting these 4 registers, we jump to play node, and we return from play node thanks to the C that we know where to return to. And so play node, we jump here, And what happens here? We have the same code like we have used until now. That's output, that delay, output, that delay, but we use here more registers. Why? Because we need to keep track on the number, for example, 370, we need to reuse it inside of here, and we need to remember this, because that's why we don't decrement L. We copy this L into, for example, register D that we haven't used, and we start working with D, but L stays the same because we need it. We need to reuse this L. We need to reuse this L. We need to assign it once again, not 255, but with each node it has different value. In our case, we cannot use everywhere 255 because the nodes are different, and we need to remember this number. That's why we're not touching this L. It's holding its number, but it's copied to D, and with D we're going to deal. And the same way with B, we're going to remember this B, and that's why we're not going to use this B. This B we copy into E, and we going to work with E, not with B. E is its copy, but with E we're working. It's going to decrement from B, from something like, for example, from 73, it's going to decrement to 72, 71 until it reaches 0. So instead of B, we're using E. And after that, we're going to refill. We're going to, we need this initial number that is 73. That's why we're not touching B. We're working with E. But all the rest is the same. And after we have finished playing, we use this C. How do we use that? That's the reference where we want to jump next. How do we use that? We jump, we take C, copy it into L. Why? Because L we don't need anymore. The node has been played. The L is free. So we put C to the L, and we use H because it's 0. It has reached from some number, for example 3, into 0. Now it's 0 here. We put this jump to HL, that means jump to HL, and HL holds, H holds 0, and L holds C. 0, that's 0, 0, 0, for example, like in Excel table we had, remember, 0, 0, 0 and and C holds this, for example, C holds node 9, that's the address of memory where to jump to. That's the way it is. You can learn it from Google, but I will put all this stuff into the folder that you reference to this folder, link to this folder you will find in the description for video number 1. So let's see how it plays, how this 9 nodes play with reusable part that's named play node, that's labeled play node, that jumps to play node, you see. And this is the part we have already, we know already, we used this. And these semicolons just for decoration. You can use semicolon, that's the comment mark. So we press F8. We have translated, by pressing F8, we have translated this language, this assembler, into machine language, and we copy this into our notepad, and we're going to Control V, that's paste. And this the last jumping doesn't jump to some number, it jumps to HL. It has we don't it has just one byte, this instruction. For example, here you see jump, this different jumps here, and one of them is HL. It has just one byte. Size of this instruction is 1 byte, because it doesn't need 2 more bytes explicitly set where to jump. It knows where to jump. That means E9 means jump to HL, and before that we have put into HL H is 0 and L is C. That's the reference to next node. So we can use, instead of jump HL, the machine code for jump HL instruction is E9. So it doesn't have 3 bytes like this one jumping. We need to put C3, and then we need to put address after that. In this case, we don't need this address. It takes it from this the CPU takes it from HL registers. And now what we're going to do, we're going to clean up this. From rubbish. You can find different this assembler helper programs from the internet, but search it for this CPU type, because different CPUs have different assembler languages. If you're dealing with this CPU Z80, then search assembler for Z80. They have free versions, they have freeware assemblers. Free of charge. This one that I'm using, it has free version that expires every hour. Every hour it shuts down. That sorry, not expires, but shuts down. You need to start it once again every time. So now we have the code. I hope I have cleaned it correctly. Only rubbish have been cleaned up. We copy this code here. Now we have 9 nodes with different delays, different durations set by HL registers, and that's it. And at the end we have halt instruction, and this halt instruction, it sits not here, not in this reusable code, but it has the last jump happens into this you see the last reference is the end, and the end is the label for halt, and the last time it jumps here and halts. Now we have to write to the memory chip. We have to instruct this guy how to write this new version of our program into the memory chip, and for that we're using Atmel Studio. So, putting it to work. Everything seems to be connected. The controller is connected with the computer with this one, and memory is connected to the controller. We have this problem once again that it's not going to communicate with the controller. Now it's done. It has worked. Now we give some more voltage here, and it knows already how to write this our last program version to the memory chip, and now it has written this new version consisting of 9 nodes to the memory chip. Now we're going to hear how it works. Yeah, we will connect the first diode input of the diode, the output of the flip-flop. Our output we will connect to the speaker. Yeah, you hear? That's our 9 notes. You can write them not using our stuff. You don't need to use this guy. You don't need to use assembler. You can just manually translate into machine code everything, and the code you will find also in this Atmel Studio. You can download it for free, this Atmel Studio, and one of the files you can open it with a notepad, for example. Just select open with, and you will find this code here, just like this. It's the same code, and you can write it by hand, but it takes a lot of time to do it using breadboard. But I hope you have understood the idea. So that's very simple if you're using breadboard and the memory chip like before, like in video number 2, but it takes a lot of time. And thanks for watching, and bye bye.